My name is Rebecca Stoll. I'm a graduate student in astronomy at The Ohio State University, and I'm here to discuss the main results of my recent paper with Jose Luis Prieto, Chris Stanek, and Rick Pogge, entitled Probing the Low-Redshift Star Formation Rate as a Function of Metallicity Through the Environments of Type II Supernovae. The question of how different classes of supernovae depend on progenitor metallicity has been limited by the lack of an unbiased standard of comparison. Using the metallicity distribution of galaxies is insufficient because core-collapse supernovae trace star formation rather than stellar mass, and because lower metallicity galaxies at a given mass are known to be more highly star-forming. We address this by creating a metallicity distribution of the Type II supernova progenitor regions that avoids many previous sources of bias. We have measured oxygen abundances at the explosion sites of a homogeneous sample of Type II supernovae from the Palomar Transient Factory. This is an aerial rather than a galaxy-targeted survey, so it does not exclude supernovae in the lowest mass hosts. Here is the oxygen distribution that we find, shown as it would be measured with 5 different strong-line abundance indicators. For the scale of the N2 diagnostic of Patini and Pagel, in black, we find that the median metallicity is 8.65. 90% of the host galaxies are in the Sloan survey photometric footprint, so we extract fluxes in the 5 Sloan bands and fit for the galaxy mass, star formation rate, and characteristic stellar age. For context, we compare the hosts of these Type II supernovae with the star-forming galaxies in the MPA-JHU value-added catalog, shown here in blue contours. The Type II supernova host galaxies, in black, trace the spread of galaxies in stellar mass on the x-axis and oxygen abundance on the y-axis. But in the plane of oxygen abundance versus star formation rate, we find that the hosts are slightly offset to higher star formation rates, as we would expect if Type II supernovae trace star formation. The distribution of local gas phase abundances of our homogeneous sample of hosts of Type II supernovae is consistent with recent studies of host metallicity of heterogeneous samples by Anderson et al. 2010, in orange, Prieto et al. 2008, in green, and Kelly and Kirshner 2011, in purple. This consistency is surprising given the very different sample selection. We measure oxygen abundance because it's observationally feasible, but iron abundance is more important to the evolution of massive stars, such as the progenitors of core-collapse supernovae, because iron produces much of the opacity for radiation-driven stellar winds in massive stars. But oxygen abundance does not map directly to iron abundance. At low metallicity, alpha elements, such as oxygen, are observed to be enhanced relative to iron in stars in the Milky Way. We define a conversion from oxygen to iron based on observed stellar abundances for stars in the Milky Way bulge, red, and disk and halo, blue, with a wide variety of metallicities. We use this conversion to estimate the iron abundance distribution of the Type II supernova sites. We find the median iron abundance is -0.6, assuming a solar oxygen abundance of 8.86. Since there's some dispute about the solar oxygen abundance, we show how to modify this result for different oxygen abundances. Assuming an abundance of 8.69 shifts the result to the right, leading to a median iron abundance of -0.39. In both cases, all of the Type II supernova progenitors appear to have subsolar oxygen abundances. All of these hosts, however, are metal-rich enough that iron, rather than carbon or other non-iron elements, should still dominate the radiative driving of their stellar winds. For more details of our results and methods, please see our paper posted on astro-ph today.